Okay, hello, good morning. Welcome to my talk on Enterprise TensorFlow. My name is Christoph Henkelmann, and well, first of all, thanks again for showing up so early. I heard it was late night last night. This talk is about using TensorFlow models in Java servers, generally in a Java environment. So you can, what I do here, you can use in any kind of Java environment, but we'll have specific examples for Java servers. That's why it's called Enterprise TensorFlow, because we all know Java is the enterprise language. And yeah, well, let's see if we can turn TensorFlow into enterprise as well. Very quickly, who am I? My name is Christoph Henkelmann. I studied in Bonn. I currently live in Cologne. I am the co-founder of The App Guys. It's a company based in Cologne. Currently, I am doing some freelance work and working on the next big thing. I mean, aren't we all? It's got something to do with machine learning. And I have 18 years of Java experience. I do a number of different languages, but Java is what I started with, and that's what I most often use in a commercial setting. I'm starting a new artificial intelligence blog called Divisio, and there you will find the contents of this talk in a blog series in much more depth. So my original scope for this talk was much too big for 60 minutes, and I noticed it, and so I will turn everything into more detailed blog posts. Also, everything I will do here, you will find there as code examples. I will put everything on GitHub, so if you don't catch some of the lines that seem important, don't worry, in a few weeks you'll be able to check them out. I didn't finish all that yet, so this is something that will come up in the next few weeks, bit by bit, so if you're interested, you can check there. Okay, before I start, maybe so I can adjust the speed of certain parts of this talk, a quick show of hands. Which one of you has already used TensorFlow? Hello World example counts, just running it, okay? Just out of interest, who's using it professionally in a daily setting? Okay, none. Which of you know Java programming? Okay. Who of you do it commercially, professionally? Okay, great. So we have a lot of Java programmers with not so much TensorFlow experience. This is great. That's the target audience. So what will we do in the next 60 minutes? First of all, we'll ask ourselves, why are we doing this? I will try to keep it as short as possible, as you all do Java. We don't need to talk about that much in so much depth anyway. The next thing is the big picture. I will just summarize everything in 90 seconds. So if you are in a hurry or you're really comfortable with everything, you can leave after that part. Everything else will be in the code examples anyway. Then comes the actual topic of this talk. How do we save our model in TensorFlow? In any sane framework, it should be a one-liner. In TensorFlow, it is more of an art, because TensorFlow seems to have 7 APIs to do 3.5 slightly similar things. That's somehow the TensorFlow AP design. So saving actually is, in my opinion, the hardest part. Then I'll show how to load and run it in Java with the command line application, which then is thankfully really, really simple. Then I will show how to integrate that in a server. If you're all Java server experts, that will actually be the obvious part, how to include it in a REST service, but I didn't know how much architecture or patterns for servers everybody knows, so I will give 2 examples how to use it in practice. Then we'll do a quick summary and wrap up, and if there's time left, which I doubt, we'll have a quick Q&A. Why are we doing this? Part 1, you have a wonderful model. What happens next? We know the first 95% of development take up 95% of time and budget, and the next 5% take 95% of time and budget. The aim of this talk is maybe to reduce this to like 50 or 75%. In the end, you always have to build a complete working piece of software. If you do Java professional, we all know that. In the end, the customer wants some value delivered, or what he thinks is value. So you have to get it somehow working in the end. And it's all nice if you have a cool IPython spreadsheet with some nice visualizations, but in the end, you have to include it in an app or a web service or whatever. Often you might have an existing system. sometimes you have a completely new product, especially for machine learning, but often you integrate into some existing ecosystem or product, and then you have to adapt. Why not use Python? We will focus on Java and Java Server, but for completeness sake, let's list what can happen, why we can't use Python. We have platform constraints, mobile, native, desktop, embedded, where we cannot use Python for one reason or another. Interestingly, embedded is probably, these days, it's very easy to use Python. In those cases, when you can't install Python or run Python, Java won't help you much either, except maybe on micro edition devices, and of course Android. But we will not cover the Android case. Google has a new framework for that, which is specifically aimed at lightweight devices, and that's a different topic. So, why not Python? There are constraints that you will probably know better. Customer requirements. You have a big customer, publishing house, bank or whatever, and they have their coding standards. You get an 80-page document about coding guidelines, which libraries you can use down to the minor version number. And if Python is not on that list, you're out of luck. There might be politics involved. The key technician you have to work with to get it into the system does not like your approach or anything, but he is a gate closer for your project. So he says, nah, all that Python stuff doesn't work, or some other reason, or someone who isn't so technically capable just, is scared or something. Or tons of other reasons, politics. I mean, it's 50% of software development, sometimes seems like politics. Maybe the customer says, yeah, sure, let's use Python, but they are a big company and they have a certification process that takes 3 to 6 months for every piece of software that has to be tested and included on their servers. So you don't have the time for that because you got to be ready for Christmas. There might be organizational constraints. Maybe you are part of the machine learning team that was hired to build the new project. You're done with your work, your contract runs out, and the people who remain and have to maintain the system are not Python people. And for everyday work, they say, well, we have to have a better way to maintain this. Other reasons might be, mainly for existing projects, you want to keep dependencies to a minimum. Yeah, you don't want to include a complete Python runtime if you already have another runtime. You have to keep the build simple. Cross-language builds are always very complicated. Keep the installer, the deployment, and the update simple. The more stuff you add to your installer, the more complicated it gets. If you have a desktop application that's written in, say, C# and you add a Python environment, that makes it really fun to write that installer and updater. You want to keep the artifact small, including a complete different language with runtime is a lot. And of course, lower admin maintenance effort. If you have a server system, have to keep 2 ecosystems up to date. That's more work on your administrator than just keeping one. And maybe you don't like Python. That's also a reason. If not Python, why Java? We can do this really quick. All Java programmers, Java's great. So nobody ever got fired for choosing Java. Yeah, that's a good reason if you have a complicated customer and you really want that project. Enterprise-ready open source. You have middle management, upper management who are not technically savory. And you say there's this one guy who has this cool machine learning solution, and he's totally hip Silicon Valley style, and you can wear a suit and say, well, yeah, that's all cool, but my solution, not my program, my solution will be enterprise ready. Because I use Java, enterprise Java. There are many existing teams. This is the existing platform thing. Often you already have a Java system, and that's it. You have to include it there. And especially where the money is. Okay. Other reasons for using Java even quicker. I'm not really a fanboy. Every language is cool. Everything has its advantages. So this is very subjective. You can say this about a lot of different other languages as well. But Java is fast. I always like it when people are proud of the performance of their Node.js server because it's so much faster than Ruby. Yeah, nice. I think you get a bit more than that in Java. Short, quick story from a real-life project. A couple of years ago, that wasn't deep learning, it wasn't TensorFlow, but it was machine learning. And we actually had a team of C++ and Java programmers. The C++ guys were really, really good. I know C++, but I know what I don't know. And those guys were far better than me. And they were actually, this one guy was working at a games company making 3D games, so he knew his fast C++. And for reasons I don't want to go into, we actually wrote the prototype in Java because it was quicker. And then the guys had to write the C++ implementation for the final product. And they didn't manage to get it faster than this Java implementation because the JIT compiler just optimized the hell out of that code. And they used inline assembler and everything. They just got 98% of the Java performance. So I mean, we're running TensorFlow, that's C++ anyway, so the TensorFlow doesn't get faster, but the whole environment. Java is very well tested and reliable. It's been around a lot. And I don't know, I did a lot of enterprise stuff. We all know that filling out 10,000 lines of XML is not always fun. But that's where Java got a bit of a bad reputation the last 10 years of being uncool and bloated. But there are a lot of new frameworks and new approaches out there. And frankly, if you use the new frameworks and new stuff for a new project, it's much less enterprisey. Don't say that too loud if you're talking to the customer, but it can be really sleek and fun. And I personally recommend this stack. If you want to have a look at it, Ninja Web Framework, my personal favorite. It's more like Ruby on Rails with Java. It's really cool, but more well-tested and faster. Juke for database, Guava. Okay, we know that anyway. So, now comes the stuff for those that are in a hurry. How do we do this? Variant 1, using the TensorFlow Java library. I call this variant 1. This is what you do in 95 to 99% of the cases. There is a Java library that wraps around the C++ runtime of TensorFlow, and we, of course, include that in our Java project. So what do? You save the model as a saved model. When you take anything away from this talk, it's saved model. This is what you need, because if you Google saving stuff in TensorFlow, you will end up with Saver. Saver isn't, despite the name, is not what you want to use for saving yourself. Okay, use saved model. Integrate a Java wrapper dependency in your project. Everybody tell me who doesn't know Maven. You all know Maven? Anybody? Yeah, dependency management. Yeah, well, it's a dependency. Then you have to get that saved model data into your server. Not so complicated. You init the TensorFlow graph. You only do that once on server start, because TensorFlow, the engine, is thread safe. That's pretty cool. You perform pre-process. Now for each request or for each processing, you do the pre-processing that's not already part of your graph. You wrap your data in Tensor objects. There's a Java class in that library that's called Tensor. You put the data in there, bam, you run and get your results. You're done. Okay, that's the talk. There is a second variant that you might sometimes need. I don't want to go into too many examples here, but maybe there's actually a reason you cannot even use TensorFlow in your Java server. Always remember that TensorFlow is not some magic that only Google can do. The algorithms in there are standard algorithms, well described, and there are tons of different implementations in other frameworks. For example, deep learning for Java. So if you're all Java guys, I didn't check it out as much as I'd like myself, but maybe looking into deep learning for Java is interesting as well. It has all the models, it has GPU acceleration. So maybe for some reason you want to use that. Then you can train in TensorFlow and export the learned parameters in a CSV or a binary file or something, and then load it in your other model. And if the algorithms are both implemented correctly, you can use a different engine to run interference than you use for training. Always remember. Also, if you're really pressed, I mean, it's an obscure case, you can always implement your inference algorithm yourself, because that sounds scary, but running inference on a neural network is really, really easy. It's just a few for loops and multiplying and adding numbers. It's nothing more. The training is really, really complicated. You don't want to implement that. I never did, luckily, except for really simple models. But getting the result is easy. So maybe for some reason, you want to do that yourself. Okay, when we do that for very rare obscure exceptions, we save the learned parameters in your format of choice. I will put a code example on the web page. It's not part of the talk. It gets too long, but it's actually easier than the other one. Integrate Java dependency for that other library you use, and then you integrate the learned parameter data. It's basically the same as with the saved model. Init your model if you have to, and do the pre-processing that is not part of your model. Again, same there. Wrap the data for your other lib, not in a tensor, maybe it's called a tensor, and run interference and retrieve results. So everything we do here, we can do with another library as well, in principle. But funny enough, it's probably easier than with TensorFlow. Okay. Now, we need to find out how to save stuff if we want to use TensorFlow. For those, I will do this a bit more in depth, because you all know Java, but not TensorFlow so much. Remember, TensorFlow is not actually a Python library for deep learning. TensorFlow is a C++ graph-based computing engine. So there is a C++ core that does all the heavy lifting and the smart algorithms. And around that, you have a Python wrapper API that allows you to build your model. Okay, that's just utility. You could do it in plain C++. It would not be fun, but technically you could do it. And what actually happens under the hood is that a graph is created. And a graph, for those, I don't know how much theoretical background you have, is just a connection of nodes. We call this, I've got the pointer here, this is a node. And for example, here, this is an example from the Google website. We have here a node that is called shuffle batch. So we have our learning examples, they are shuffled. And then the data goes through these edges into a convolutional layer. That's some kind of neural network. And into another one, and into a node that's called local 3. I don't know what it does. And up here we have a softmax linear that actually calculates the results. This is how TensorFlow looks under the hood. It's actually, that's why it's so flexible. You can connect those nodes in any way you like. But that is actually done in C++. You just need the Python stuff to build this. Python code is just a convenience API to build and run this stuff. So what do we need to save in order to run our model? We need to save the structure of the graph, obviously. We need to know where is which node and how they are connected. We need to save the learned parameters. In the previous slide, I had this node with a convolutional layer. When the network trains, it learns a lot of float values for all those connections inside the neural network. And of course, those float values, we call them parameters. Even if you don't set the learned parameters, you have to save them, obviously. Because if you just save the graph, all the floats will be 0 and it will do nothing. Sometimes you have additional assets, like dictionaries. If you do some language processing, you might have a dictionary that maps numbers to words, for example. The signature of our inference. I'm using this term inference. You could say running making predictions, making regressions. Inference means I throw something in and something drops out in the end. Nothing to do with learning. The signature is, if I have this really big and complicated graph, I need to know where to actually throw things in and where they drop out at the end. It's like a function signature. What are my parameters and where's the results? And those graphs can get big, so I need to know the names and the parameter types of the nodes I actually want to use. Sometimes hyperparameters. Hyperparameters are the parameters we set ourselves as programmers. For example, the number of layers in our neural network. Some of these parameters are obviously part of the graph. If I construct a neural network with 10 layers, my graph will have the 10 layers, so I don't have to save them anywhere else. But some hyperparameters are numbers that are stored somewhere else, and I need to set them in the graph for my model to run, so I need to make sure those are saved as well. So now we come to the API. I got an image of the TensorFlow persistence API design philosophy for those who do dabble a bit in patterns. And stuff. I think the technical term for the TensorFlow RP pattern is big ball of mud. So what they actually do is they have this big ball of goo, and every time they need a new method, they slap it on somewhere, and they try to keep the ball nice and round, but it's just that. So it's a bit hard to find your way around, I think. I've talked to a lot of, I always try to, maybe a bit arrogant here, a bit spoiled, so I talked to a lot of people on this conference, and I can tell you I'm not alone with that opinion. So, which API do we use? I just said there are partially overlapping APIs. Sometimes one API uses the result of another API. They are in different packages. It's a nightmare. Long story short, use saved model. That's also the stuff that you're supposed to use in the future. One thing before we come to the Java part, everything I say here is also applies to the TensorFlow serving library. Google has a recommended way to serve TensorFlow models in Python, and when you want to use that, you use exactly the same stuff. So up to part 4, everything applies to other languages, C#, etc. as well. If you construct your models, if you build your actual product, we have seen a lot of IPython sheets. I always start with them as well. They're a good way to start your model. But if you really want to work with them later and save, use the TF estimator class. I will show you later how to use that. I will use a prepackaged one. You can write your own ones. It's a bit more complicated at first, but in the long run, over the project, it will make things a lot easier. So what is the saved model? A saved model consists of multiple metagraphs, one or more, and one checkpoint. Okay, that doesn't help us much. So, what is a metagraph? A metagraph is a graph, that's the structure I just showed you, plus the signature, that's why it's called metagraph. It's a graph plus additional information, and assets. And one important thing, the metagraph does not contain the variable state. If you just save the variable metagraph, all your learning is for nothing, because it's empty. assets, as I talked about, dictionaries or anything. I hardly ever use them. So the checkpoints is interesting. That is the state of variables. That's what we actually learned. The question is, why don't we save the checkpoint in the metagraph? If you have a really, really big network, like 250 layers of convolutional network, you easily run into megabytes or hundreds of megabytes, sometimes I think even gigabytes of variable data because the networks are so large. Now imagine you have two ways to make your inference, for example. And you save two metagraphs. That's why we have two metagraphs, because maybe you want two different variants to do your prediction. If we save the checkpoints with the metagraphs and say the checkpoints is 500 megabytes, each of our metagraphs would be 500 megabytes, we get a gigabyte of data. This is why the checkpoints are shared by all metagraphs. So if two metagraphs have the same variable, it's only stored once in the checkpoint. So how to create a safe model? There are multiple entry points, there are different APIs depending on what you use, and sometimes automagic things happen. We just use the estimator that has a method to save. And the good thing is about estimators that while you're training, they will automatically save your state from time to time. So you can train a bit, and maybe you don't have enough CPU hours, or your machine runs hot, or you just want to shut down your gaming server to play gaming machine to play some game. And you can just stop training, and everything will be automatically saved, and then you can just start again, and you don't have to worry about that. That actually works out of the box if you use estimators. This is actually what the saver does under the hood. But these saves, for some reason, I can't imagine. I can't imagine why, but they can't be used by the Java code. So Google thought it was important to have two different save formats, one during training and one during serving. I checked other frameworks; they don't do that, I think. Okay. So how do we use an estimator? So this is a lot of code to put on one slide. You can blur your eyes a bit. Most of it you don't need it. It's just to explain the principal idea. If you use an estimator, you have to build a so-called input function. This is this down here. An input function takes no arguments and returns tensors with the features. This is what we put into the model, and the labels. This is what's trained on. And the typical pattern that you will see, so you understand the examples better, is that you have a function. We are in Python, functional programming. We have a function that gets a lot of parameters. And these parameters depend on what we want to do, how we have our data. If our data is in a database or in a file or whatever. And we put the data in here. Here we have a little utility function to decode CSV. And here we build graph objects to actually put our data in the graph. See here this shuffling? That's the one we had on the graph as well. So this is all helper stuff, and in the end, you return a function with closures to this. So for Java people, maybe better to understand this is a factory that gets parameters, and in the end, we return an instance of an interface. That's it. That's how it works. You can do it in different ways. This is how most examples are structured. I recommend you do this. So now things get a bit easier, more comments, less code. Another thing you need to know if you use estimators, forget about the feature columns for a moment. That's a way for this particular estimator that I use to know what is the input. More interesting is this. It's the run config. That's another class. That's funny in TensorFlow. Sometimes you have a function-based API. Sometimes they use objects and classes. I don't know. The run config is just a bean, we would call it. And here you have some info how you want to run your training, how often to save, how often to log. That's pretty useful class to make your life a bit more pleasant when you do the training. I recommend you use run config from the start. Another nice point of the API design, run config has a member. That's actually, it sounds boring, but you will spend a lot of time looking for this and asking yourself how it works when you actually try to do it. So I put it on the slide. Has a parameter called model_dir. The model_dir does not save the model, it saves the checkpoints. Okay? And to make things interesting, when you build your estimator, you pass the run config, where you save the state, and that also has a parameter called model_dir, and they do the same thing. One of them takes precedence over the other. I don't know which one, and I don't want to know. And this is why I put just everything that's config into run config. I don't know why they put that parameter there as well. I have no idea. Okay, and in most cases, if you just want to try things out, you can use one of the prepackaged estimators. So in most cases, you want to try deep learning, you don't have to learn how a neural network works. Well, you should a bit, but you can just use some prepackaged estimator, and they have well-documented or more or less well-documented parameters. You just build this instance. You give it, in this case, your feature columns. I have here some, I have 4 columns that I use. Here's some parameters for the neural network. You can play around with them. These are the hyperparameters I was talking about. And you then just give it the run config. Again, not too much detail, but this will all be in the examples. And now what you need to do is you have to build an input function. Remember our factory method? We call it. And our training we do on this CSV file. And these are just some methods I came up with. I want them to be shuffled. I want 100 repetitions. And then we have our input function. And training is just this. You have seen the other examples in the IPython book. They often use this session mechanism that happens under the hood here, but if you use estimators, training is just one line. I wish everything else was so easy. And then in the end, when you're done training, you want to try out how to test your code. And then you obviously use it. Normally we should use validation sets as well, etc. I will skip this part. This is not best practice here. It's just for showing this. We have a test file, and we use the same factory function to use our build our input function. We just give it different data. We are in Python, so we can leave parameters out. We have default parameters. And then we evaluate our results. So first we train, and then we see how good our results are, and then we get a summary. So now we want to save our stuff for serving. Now it gets really interesting. You would think that we build a third input function that defines how our data gets into the graph during serving. That is not the case. For some reason, we have a different API to define the input function for serving. And there are a lot of ways to build this. And what you need to end up with is a serving input receiver. And this is quite the rabbit hole, because all the stuff currently is not. There's a lot of stuff in the API that's completely undocumented, just no doc strings after all. A lot of trial and error. The good thing is, in our case, we just need one method, and this is it. It's the build raw serving input receiver function. And with this method, that's just a global, we would call it static method. And all you do is you give that a map. This is a way how to define a map in Python. We have a string. That's the key. That is the name of our input parameters. Then we use a placeholder object. When you dig into TensorFlow, this is the classic way to define variables for your graph. And we have to repeat the name here. Don't ask why. In our case, we just have single floats, so they don't have any shape. And then we have the serving input function. And then we call this method to save our saved model. The saved model is not saved in the model dir, it's saved in a subdirectory of export dir base. I don't know why it's not called saved model dir. Then we give it our serving input function that we just built. In some cases, you might have additional stuff that you want to save with your graph for some reasons. This is this assets extra. It's basically you can throw all kinds of files or anything you want in there. You hardly ever use it, but I just thought I'd put it here. So you are not confused what it means. You can choose to save binary or text. For debugging, sometimes text makes sense, but you want to use binary here for most paths. And then there's this checkpoint path. You remember the checkpoints that were saved during training that we need to save with our model, because otherwise the network will just be empty. This is here, but you don't have to specify it. If you don't specify it, the estimator remembers what model dir we gave it, and if you don't specify it, it just uses the last checkpoint. And in 99% of the cases, that is what you want. If you want to compare certain stages of the training, you can pass a different checkpoint here. Okay, what is created? It's not a monolithic file. What is actually created is, first of all, the checkpoints during training. They look like this. We have a folder called checkpoints. That was we passed. This file simply contains the number of the latest checkpoints. It's just a text file containing, in this case, 31,250. This events file is what you use for TensorBoard. If you ever get started with TensorFlow, very soon I recommend you look into TensorBoard because it makes your life a lot easier and it's a lot of fun. It's like a debugging web UI for your learning. This is the actual graph. Remember, not the meta graph. This is just the graph. And here are our checkpoints. No signatures or anything. Okay, the saved model is a bit different. The saved model always gets a timestamp, so if you call it multiple times, you get multiple timestamps. You have one big PB file. PB is protobuf. Anybody here already worked with protobuf before? A couple of people. Protobuf is basically, it's a binary JSON format that Google uses for all their products. Google uses it everywhere. Everything you use internally in Google, they all use protobuf. If you know web services, if you know like interface specifications and JSON, it's just a variant of that. You don't need to know how it works. That's the good thing. But you can debug it, actually, and when you save it as text, it looks a bit like JSON. And here is our variable state. Those are the checkpoints. The checkpoints are, in this case, not called checkpoints anymore. They're called variables, but it's the same kind of files. Keep things interesting, you know? Okay, saving for another lib. We make this very, very short, just so it's on the slides. You can look it up later. I talked about running things in a session. What you can do is you can also evaluate any node in your graph in a session. And when you do that, you get the float value or the array or the tensor of that node. And you can just say evaluate the neural network, not running it, but getting its parameters. And then you get a big float array with all the contents, and you can just save that. That's what you do. It's actually much simpler than saving in saved model. If you know how to use the checkpoint files, I haven't figured out what format they are in. I suppose it's some protobuf format or just a big blob of floats. I haven't found it out. I didn't find any documentation. If any of you find out how the checkpoint files work, tell me. I'm really interested to know. If you don't know the variable names you need to save, look in TensorBoard. You will get a nice big graph of what you built, and you can just browse it and look what the names are. Because those estimators we use, they create all the variables automatically, so we don't know what their names are. I mean, that's just a suggestion. You can CSV is not too large or binary or compress or whatever. Okay. Now we are leaving Python land and entering Java land. I don't know, need to tell you who that is. So everything from here on is Java. As I said, the previous stuff, you can all use that for C# or TensorFlow serving as well. Now we look in how to do things in Java. Okay, add the TensorFlow Java wrapper to your POM. That's simple. The good thing is, this wrapper, and this is very important information, contains all the native libs for macOS, Linux, and Windows. So I don't know if it's for BSD as well, but in most cases, it's just one jar that contains everything. You don't have to care about anything. You don't have to install any dependencies, binary on the system, no Python, no nothing. It's just one jar and contains everything. But it only contains the CPU version of TensorFlow. But that isn't bad because we don't do training in Java. We just use inference. And in most cases, actually, if you don't use too large batch sizes, CPU inference is often faster than GPU inference. Because the GPU really starts to shine if you take a lot of data, throw it in there and shove it through the pipeline in one go. But we're doing REST requests, so we want this to be responsive. And so, funny enough, CPU in this case is often faster. And not every server, they are getting more, but not every server has a TensorFlow or CUDA-enabled GPU. Yeah, for inference, that's enough, and sometimes even better. If you need the GPU variant, and you're a brave soul and know your C++, you can just build the library yourself. There is actually documentation on the Google site. I looked at it, and I hope I never have to look at it again. It's your classical thing, building something like that by hand. And then, for those of you who are JNI buffs, it's probably really easy, but I've found it a bit scary. Hope I don't have to do it. Okay, this is your dependency. No need to write that down. You can just Google that. I wasn't sure if there are non-Java people here, so I put it up. You have seen this before. Okay. We will, in a moment, switch to Eclipse. Yeah, you can tell how old I am, that I still use Eclipse and not IntelliJ. We are loading the saved model from a folder. So what do? We need the path to our folder, obviously. And then we need the serving tag. I will come to this later, what this magic string is. And now comes the Java API. Remember all that horror with the TensorFlow API, how many variants there are, and all those parameters? This is how we save it. Isn't it nice? One-liner. That's it. And you only have to do it once, and once you loaded it in your virtual machine, you can reuse it again. You don't have to load it every time. Yeah. Thing is, that's actually the C++ API that does the loading, so we can't use any input streams or anything. So we have to load from the file system. That's a bit nah. What is the pros? It's simple. Everybody understands the file system. And the model can be updated without redeploying the server. So maybe you have a big model, and then you put it in a network share that is mounted on all your servers. You check regularly if the timestamp has changed, and if it changes, you just reinitialize. So you can actually reinitialize your TensorFlow model on running servers without even rebooting the servers if you do it that way. I mean, threading issues, yada, yada, yada. We just do that correctly, and everything works. This is good for huge models, because if you want your var or jar, you certainly don't want a 500 megabyte neural network parameter blob in there. But often, remember the talk, the introduction on Monday, that was really great. I don't know who of you attended that workshop. The simple models often do the trick, and they do it really nice. Start with the simple models first. Everybody wants to do deep learning, even I often skip the part with the simple models, but you'd be surprised how good the simple models can be if you do it right. And they are small, they are fast, they are better trained. So before you run everything through a neural network, TensorFlow has all the classic machine learning algorithms as well. So in that case, your parameter data will be tiny. What's the cons of this approach? Annoying deployment. I mean, we just said we want a simple deployment, right? We want one WAR file, so definitely don't want our admin having to mess around with a bunch of files in a folder. It's just unelegant and makes packaging and updates a bit more cumbersome. So, another way, how do we load it from the resources? Most of you will know this thing. We can our wars and jars are just zip files. We know we can just add anything as a Java resource that we want. So we just throw it in there with a jar or war. And the thing is, what you can do in a static initializer or somewhere else, there's an API call, I didn't include it here, where you can create a temporary folder. I don't really know, it's in Java I/O somewhere, and you can create a temporary folder that's tied to your virtual machine. And you're guaranteed to be able to read and write in it. So what you can just do is you create the temp folder, stream your resources into the temp folder, load them with the API, and then your temp folder will be deleted automatically when the virtual machine shuts down. I've done this for other cases where I had to, move around a little and use a native API that just knew to do file system, and it works quite well. So it's, we can, what are the pros? We have only one artifact, so deployment and everything is like we are used to doing it. Folder gets automatically done shutdown. What are the cons? I mean, this is not nice. Let's be honest. Okay, it's a bit hackish. So how do we use the Java wrapper? We just saw how we load, but how do we run it? The running we do in Java actually looks much more like you see in most IPython examples, or Jupyter, I think it's called these days, where you initialize a session. So TensorFlow has the concept of a session. And you can just initialize a new session. That's a pretty cheap and quick operation. And then you put your data into tensors, and you run the tensors inside your session. And that's what you do in Java as well. Remember, it's thread safe, so if we have we process multiple requests at once in our server, every request can just create its own session, run it, and you're done. You wrap your values in tensor objects and unwrap the result. So how is this done? And now we switch to the code example. I've all prepared it ahead, so I don't do any live coding. So this is can everybody see the code okay? Big enough? Okay. This is a simple command line application. Here's the code we have seen before. This is just where the model is. This is our serving tag, and here we load the model. This is a static utility function that I just wrote for myself to wrap one float into one tensor. Okay, this doesn't look too nice, but you put it in one utility function and then you're done. So you see here that there is a static constructor for the tensor. The first argument is the shape. You remember tensors are just arrays with multiple dimensions. Mathematically speaking, there's something else, but for our intents and purposes, it's just a big array with multiple dimensions. So here I don't know what's along, but here we just tell how many array axes there are. We have just one float, so we have one axis, and that's just one element long, so 1. Then we use float buffer from I think it's NIO. Yeah, it's NIO. That's basically, float buffer is often used, I think, for JNI APIs to pass float, just memory pointers of data. And here we create a little float array, put our float in there. That array is again wrapped in a float buffer, and all this is wrapped in a tensor. So, and when you do that, you have a simple main method. I was even too lazy to pass the arguments. I mean, obviously, you can read this from the command line. These are just some test values I used for testing to confirm that the float I get out of the TensorFlow engine here is exactly the same. I mean, you have to get exactly the same IEEE float. We're using Java. It's the same floats as in C++. So everything that drops out here needs to be exactly the same if you print it as in TensorFlow. And this is why I put it here. And then running is pleasant. We have our bundle. This is what we loaded. We have a nice fluent API. So I think the guy who wrote this wrapper is not the guy who wrote the original Python API. Then we create a session. In this session, we create a runner. I think if you want to run multiple times, you can reuse the session, but often we will just do one request. So we just throw everything away again. And here's feed. Here we bind our values to our variable names. And now in my case, it's this model is actually not working at all. I just used it for testing purpose. It's still in production. I have 4 variables called PE, PB, ERIS. Doesn't matter what they are. They are 4 floats. And I just feed into each of these variables in the graph the value I just wrapped here. And then I fetched the results. The question is, where does this magic string come from? You need to know the name of the output variable. We see that in a moment. We run it. We get the first element. Here we get you can actually fetch multiple nodes. So if you have a complex graph that calculates multiple values, you can get all the values at once. In this case, you would add multiple fetch statements. And here you get a list of tensors. And this is just the get option of operation of the list. And here we print the results. Yeah, unwrapping is again a bit complicated, but you only have to program it once and then you're done. There is a copy method where you can simply put everything first into a float array. For some reason, this is a technicality of the estimator I used here. We only have one result, but we have a 2-dimensional array. So it's a 2-dimensional array, but every dimension only has one element, so it only contains one value. And we just output that value. So this was the command line version. And frankly, if you know your server framework, now you know what to do. So I will do some examples. I think for you, probably the server examples aren't that interesting. Another quick question, who of you does Java server development? Just a few people? Okay, cool. Then it might be interesting. That's good. That's good. I just was a bit worried that the last slides might be too boring for you. Okay, we just saw how do we get the tensor names. The input variable names, they were pretty clear. Those are the names that we chose when we built this interesting saving function. So those are just the strings we chose, and you can write them on a piece of paper and pass them to the guy who implements it in Java. So no fancy stuff here. But how do we find out where our if you write your model yourself, obviously you will also know what the output is. But if you use one of the prepackaged models, how do you find out where to actually get your result in Java? Well, we remember that our model somewhere contains the signature of our graph. There should be a Java API, but you can't query it from Java. There's no way to find out what your signature is in Java. You have to know it ahead of time. But there's my pointer. The cool thing is there is a very, very useful. The thing about saved model is actually it's pretty cool. It's just not documented very well. If you know how it works, it actually starts to be quite nice. If you install TensorFlow somewhere deeply buried in your TensorFlow installation, this is on my Mac. On your other machines, you have to find out where it is a command line application called saved model CLI for command line interface, and this is various parameters. So what you can do is you just tell it show. Tell it where your model is saved, and then it will tell you things about your saved model. And this is where I got my serve tag from. It's always called served in the case that I have here, so you don't have to find that out yourself. But remember that we have multiple metagraphs, theoretically. In our case, we only have one. They are identified by these tags. And you need to know which of the metagraphs you want to use. So if you are so advanced that you have multiple metagraphs in your model, you need to use these serving tags. Okay. Once you know what the tag is, you can get more information, because then it will tell you which signatures it contains. I think one metagraph can contain multiple signatures. I only worked with the case where I have one metagraph and one signature, so I have to admit I'm not really sure how the mapping is done here. But this is what you need. The funny thing is you don't need it in the Java code. I don't know why. I haven't found out yet why you don't need that magic constant. And now we still don't know what our variable names are, but now we know our serve tag, we know our signature definition name, and now this command line application can tell us what the input and the output tensors are. The input tensors are boring. I abbreviated here because that's the names you chose yourself. But here it gets interesting. See, the given safe model signature graph contains the following outputs. Predictions, and here's the tensor info, and here is the name. And this is the name you need to choose in order to get the result from your Java code. Okay. I wanted to make a really nice slide about how to do your pre-processing, etc., etc. It just didn't fit into the 60 minutes, and yeah, well, do not forget your pre-processing. The one thing you should take away is, remember that pre-processing is, frankly, 60 to 75% of your whole engineering when you do some machine learning stuff. Proper pre-processing is really important. And if possible, you should build your model and your graph, so the pre-processing is part of your graph. The advantage of that is, like, you need, for example, to normalize your input values. So they have a nice Gauss distribution. The thing is that has to happen when you run it in production as well. And the best way to make sure it runs exactly the same way is that you make it part of your C++ graph. Because then the guy who does the Java code doesn't need to know about your pre-processing. There's a lot less communication involved and a lot less ways of error. But sometimes, because it's too complicated to do it in TensorFlow, you do some manual pre-processing in Python, for example, or you do some manual pre-processing on your data files. Keep very, very close track of how you pre-process that, but because you have to apply the pre-processing in exactly the same way to your input, or your whole model will be useless. Especially if you, let's say you have some numeric value, okay, and in practice it lies between 0 and 10,000. Typical thing you do is you squash it to the range of -1 and 1, for example, or from 0 to 1. Now you have to know your parameters you use to get that distribution. And you have to use the exact same normalization values for your input values. Even if you train from 0, say your training set only contained values from 0 to 10,000, and in production you encounter a value of 12,000, you still have to make sure that the resulting value should be 1.2, I think. So make sure that everything that is not part of the graph is properly re-implemented in Java. If you do this, I recommend you write some unit tests for that and really check for the numeric values. Okay, I don't need to tell you this. If you do anything with images and you need really a lot of performance, I've worked on a system for years that had to do a lot of image pre-processing. You should include Java Advanced Imaging API. It's not the nicest API, it's pretty old, but it's incredibly well tested and really, really fast. So if you need your integer RGB values out of an image and make things faster, I just added this because deep learning is often used for image stuff. Use Jai. Yeah, same normalization as training data. Okay, I don't need to tell you about server-side frameworks. There are lots of them. Which ones are good or bad? It's so much personal preferences. Some are more verbose, some are enterprises, some are hip, some are new, some are old. Yeah, let's skip that. So now we know how to save our data. We know how to initialize TensorFlow, add our dependencies. We know how to load our data. We know how to run it in a session and get the results. So now comes the last part: how to implement it in a Java server. There are, of course, multiple ways, and in practice you will have variants of it depending on your specific needs. But three broad categories you can say. Blocking. That's the simplest thing of all. You send data to your server, and the response blocks until TensorFlow is done computing it. In most cases, inference is pretty quick. It takes only a few milliseconds or even 1 or 2 seconds. So most of the time, you're pretty happy with just sending data to your server, wait till it's computed, and just send it back. Just a blocking REST call. Just in case your model is either very, very complicated, or you allow a lot of data to be sent at once, or you want to prevent your server from being bogged down from too many requests, you can use queuing. So what you will do in this case, you send your data to a server, and then there are multiple ways to do it. In my simple example here, I just return a token to the sender, and the sender can check if the processing is done with this token. That way, you can implement, in my example here, I just have a thread queue depending on the power of your server. You start a queue with 4, 8, or how many parallel processing threads, and then everything gets enqueued, and you have up to 4 operations at once. And depending on how much requests there are coming in, it takes longer or shorter until the user gets its result. Batching. Well, this is also some form of batching. With batching, what I would mean with batching is the real simple case where you just transfer a big file. So I would say batching is a bit like queuing, but for really, really large amounts of data. Okay, you have 500,000 customer accounts, and you want some evaluation on those. You shouldn't call a REST service 500,000 times. That's not a good idea. You just put everything in a zip, maybe upload it via SFTP or some web service, and then you wait, and at some point somewhere you get the result back, probably also in a file. Okay, we have 2 examples. The first one is with Apache CXF. Apache CXF is a web services framework. So this is what you want to do to build microservices, middleware, REST services, SOAP, etc., etc. It speaks a lot of formats, which is cool. So you can build an interface between a SOAP web service that transfers it to a CORBA call or whatever, and has multiple transport layers. So you can do REST over JMS if you want to. I don't know if that's sensible, but it's very variable here. And the good thing is, why I chose it, it's one of those more modern APIs. The first web service I wrote was, I don't know, it was 10 or 15 years ago, and that was an XML nightmare and never worked. Well, in the end it worked properly. It was a lot of pain to get there. And CXF makes things a lot easier. Okay, I have a code example for that as well. Oh, I need to think the Q&A will be very short. Okay. Yeah. Source main Java. There we go. I don't want to go too deep into the details of CXF. Now, where's my XML? I also chose CXF because in some ways it's a traditional enterprise program. First, you need to have a beans XML. Okay. Now we feel has this warm, fuzzy, safe feeling, doing things the enterprise way. Here we define, I wanted to show you this because this is a different way of loading the bundle. It's just one suggestion how to integrate the saved model into your server. We see here we define a Spring bean. Some of you might know it. Spring is a popular server-side framework. And the beans you can use globally. This is basically a singleton. We define a singleton in XML. We give it an ID. We tell it what class to load. This is just done via reflection. And then we tell it how to build the bean with this method. And we have our 2 arguments. I mean, you definitely shouldn't put a path like that in your server specification. So, okay, it's just for example, for reference. You replace it by something more standardized and better communicated. Okay, and now the thing is, we want a REST service, and that is also not too bad because we just say we want a service. We use JAX-RS. That's actually the underlying implementation that CXF uses for REST services. And here we have our service. This is our TensorFlow REST. I just called the class TensorFlow REST, contains our complete TensorFlow service. And this service is actually, again, just a simple bean with one setter. And here we make sure that the saved bundle ends up in our REST service because we defined it with the ID saved model here. Spring will know to call this setter. We will see that in a moment. This is one, yeah, I don't think I even need it at the moment. Yeah, I left it in. This was from the original code. Have to test if I can do without. It was late. I didn't want to, it was working, so I wasn't really going to check if I need that bean or not. Okay, and now we just need one Java file. So CXF, pretty sleek. If you just want to quickly a REST server up and running for your TensorFlow, that's all you need. Because what we have here now is our class. You see, I don't have to implement anything. All I have to do is this annotation. So CXF will know what URL to serve it under. And here we have our setter. So the Spring dependency injection knows where to put our bundle. This is our helper function we saw before. And this will look familiar to you because this is exactly the same code from the command line application. The only difference is now that we don't hard-code our values anymore. We have a REST service, a GET call. So we tell CXF we want a GET call. You can use POST here as well. We tell what subpath we want. We tell CXF what is the output format. We only have one float, so I didn't use JSON here. Okay, so it just produces a string. And we give it a name, and here we have our URL query parameters. I will show an integration test for that in a moment. And then we just feed it, get our result back. So you see it's literally the same code as in the command line application. We just have to put some annotations here to turn it into REST service, do some Spring dependency injection, and we're good. Okay, time is pressing. Yeah, well, there is an integration test. I'm not going to run this all because Maven will download half the internet before the talk is over. So just trust me, it works. It says, okay, all tests pass. Here is an integration test for CXF. You have to fire up the CXF server. You run this integration test. You give it here. You see this is a simple URL with query parameters. And then we just assert that our result is exactly what we expected. And we have a running REST server. Okay, that was this example. Sorry, I have to skip this. Okay, the next example is a bit more complicated. I chose Ninja for it. It's a bit exotic. Who here knows the Ninja web framework? Nobody, great. Okay, thing is, it's a bit of an outsider framework. It's relatively new. It's inspired by Ruby on Rails, but underneath, it's all that you know. It's similar to Spring or any other framework. It uses it uses Juice for dependency injection, uses all the Apache library, you know. I chose it because it makes for very short examples. I chose it because it's really cool and I think people should use it more. It's open source. I prefer it over the classical enterprise stuff. It's lean and mean. It's similar to Ruby on Rails. But underneath all the libraries it uses, the dependencies, it's everything you need know from standard server development. So there's nothing new. It just combines it in a way that makes it much, much more fun and quicker to use. And yeah, I would use this more for web applications and web pages. You can really quickly build REST services with it as well. But it's not like CXF where the focus is more on middleware and stuff. This is more like standard web development. It's my personal favorite. It's my talk, so I thought, well, I could just use it. One thing, watch out, I don't know, it's always a topic, but if you speak to some Java developers who know it longer, I remember when Hibernate was new and we were all happy that we had such a nice persistence library. And then we had to use it in real projects. And man, there are some months of my life I want back. I absolutely despise Hibernate. And regrettably, like in most frameworks, it's also the default in Ninja. If you want to do some database work, think twice. You can just put Juke in there. Saves you a lot of time, nerves, and makes it a lot more fun. Okay. Oh, of course, the code example. Okay, only 5 more minutes left, I think. Oh, 3. Oh, damn. I knew I was a bit... queuing. Okay, there's the queuing. Here is no XML. Ninja doesn't do anything. You can do stuff in XML, but most of it is convention over configuration. So you just have Java files with a certain name. Here, I wanted to show this different example also because Ninja uses Juice for dependency injection. This is a bit different. Here, we do everything in Java. What I made here is I wrapped the whole TensorFlow stuff into a TensorFlow wrapper. The reason is I wanted to show how to batch, how to process more data at once. So I had more TensorFlow code, so I put it all into this one object. This is just a singleton. You see here in juice, we define that it's a singleton, and saves the way we saw before. Here we don't hardcode the path. We put everything into the Ninja properties. Ninja has a properties file where you can define stuff. And the rest should look similar. The only thing that is pretty interesting to you here is that we now have, because we allow batch processing. So we can put in 200 examples for inference. So our arguments are float arrays, not single floats. And our output, of course, is also a float array. So the packaging is actually pretty similar. The only difference is that here we don't have to wrap a single float into a float array because it is already a float array. So that's easy. And yeah, feeding is the same way. You see that we bind this array only once to the variable because we have tensors, and tensors can have a variable length. So even if we have multiple values for our inference, we just have to bind it once. And here, of course, the flattening, that's what I call flattening, wrapping it, peeling it out of this two-dimensional array is a bit more complicated, but that's also something, yeah, it's easy to figure out, especially if you can just copy the code. Yeah, and then we have, in Ninja, we define our roots differently. Here we have an object where we just say which path in our server here gets bound to which method in an object. And then we have our bean, and this application controller, I will just show you the queue part. Here we see we get a lot of requests. Inference requests is just a bean with my 4 values. Because I have multiple requests, I have an array. Ninja automatically unwraps that from JSON. You don't even have to touch it. If there is too much data, I send a 413. I mean, it's okay to ask for a few hundred results, but we don't want to process 2 million requests at once. And if everything is okay with the input data, we create a UUID that will be globally unique. We in our queue, and we just return the UUID to the user. For the queue, well, we don't have the time anymore. It's just in-memory processing on parallel threads. You can look at it if you're interested in that in the source code. But what I basically do is I just run an executor service and do multiple at once. This is not a good idea if you have multiple servers, etc. You should do some other queuing mechanism to get your data across your server. Oh, no. Okay, that's about it. Well, we all know how batch works. Just very quickly, if you have to build a batch processing, often you don't have to program anything. Remember, the CLI application I showed you, it can also run inference. So in some cases, you can just build a quick shell script that unzips something, runs it through the command line interface, and just puts it in another folder. So you have to write a quick batch processing. It's probably simpler just to use the safe model. You are Java people. This was for Python people. You don't need that. Things to remember. That's the last thing. Wrap your model in an estimator. You start doing proper production code. Look at this class. Look at the documentation if you find it, and use this. Export a safe model. Use the wrapper. Load the folder. Run your model. Okay, so that's it. If as I said, the code examples, I didn't clean them up and finish them. I should just take a few weeks, well, hopefully only one, to get the first examples up there. And over the next few weeks, I will build more and more complicated examples where I use deep learning for Java instead of TensorFlow for running, stuff like that. So you can see all the various variations, and I will also build a Spring one. Maybe if you're interested, if you have a framework of your choice that you really want to see, drop me an email, and if I find the time, I will cook up a quick example to help you. Yeah, well, that's it. Sorry, no time for questions, but.